All right, AP students, welcome to your AP problem walkthrough. We have just discussed Lewis structures, resonance form, and formal charge. These are, of course, the illustrations for understanding how molecules in a covalent bond share or slash distribute their electrons or valence electrons with other atoms. And it also will give us tomorrow's lesson will be about how we can predict the actual 3D structure of it all from this 2D illustration. So what we have here is we're going to do again a conceptual walkthrough on a couple of the big concepts. Lewis structures is incredibly important for the AP exam and just basic chemical understanding. Like when you go into advanced chemistry, organic chemistry, you're just going to be drawing Lewis structure after Lewis structure after Lewis structure, and you'll learn a shorthand eventually, so it's a little faster. But for the most part, you really do have to know your Lewis structures. So that being said, I actually highly recommend for this video that you watch the conceptual plus the AP problem walkthrough. But of course, I will link the description in the description box the time when I start doing the AP problem, which is the problem I would check if I were to do a homework check the next day. All right. So page 2, I'm just going to do one example in question 6. I chose OS F4. That actually has a unique name to it. So I'm not even going to tell you the name. It doesn't really follow standard rules. It follows a different naming rule called the IUPAC system. Don't worry about it. So what we have here is we have sulfur is bonded with oxygen and fluorine 4. And why I know immediately that it has to be sulfur as the central atom, by the way, is because remember that central atoms, while usually are written first, the more positive one, here we have oxygen. Oxygen is very rarely, if ever, a central atom because central atoms tend to be, okay, central atoms tend to be more electropositive or at least less electronegative, more electropositive or less electronegative. So we see here that oxygen and fluorine are both highly electronegative atoms. And we also know that sulfur is in row 3 or above, so it can handle an expanded octet. And what we see here is whatever the central atom would have been, right? If you didn't know if it was sulfur, you know that it's going to have 5 bonds to it, which already exceeds 8, the valence electron octet rule usual count. So what we see here is you have to have a central atom that can handle more than 8, and that would of course then be sulfur. So that's just kind of a little background about how to even start picking up information based off of just the chemical formula in order to construct your initial skeleton for the Lewis structure properly. So first things first, when drawing Lewis structures, and again, I have a set of rules that you should really follow, okay? The way I introduce the rules in class, I wouldn't stray outside of the order of going through those rules, okay? Because it will guarantee that you identify correct and valid Lewis structures, including all the valid resonance forms that can also develop, but that way you never set yourself up for failure in drawing an illegitimate Lewis structure. So what we have here is rule number 1, count your total amount of valence electrons. So for my total amount of valence electrons, sulfur, okay, each sulfur, or let's start with oxygen. Each oxygen brings in 6, all right? Total valence electrons, TVE. Each oxygen brings in 6. Each sulfur brings in 6 as well. And each fluorine brings in 7. So what we get is a sum total of 6 plus 6 is 12 plus 28. We get a total of 40 valence electrons available to us. Now, once we count the total amount of valence electrons, now we develop out our skeleton. So again, using my previous knowledge that I just walked you through about how we know that sulfur is going to be the central atom in this case and not the usual first element written, we draw our skeleton where sulfur is in the center. And we have fluorine, 4 fluorines attached to it, and 1 oxygen. And right there, we count how many electrons we've used up. Because now at this point, once we've counted the total amount of electrons, all right, once we counted that, now we redistribute accordingly. Okay, we don't have to feel like we're stuck to only give a certain element this amount because it came in with this amount. No, we just totally redistribute, start all over, redistribute accordingly. So I've used up in the skeleton, I've used up each single bond, being 2 electrons. I've already used up 5 times 2, 10 valence electrons. So I'm down to 30 valence electrons to distribute. Now what I do is I go to my terminal atoms, my atoms attached to a central or the relative central. Sometimes you look at a huge chain of a compound and you just pick one atom to focus in on and do, relatively speaking, this is the central and you fill out the terminal, right? So here our terminal atoms are 4 fluorines and 1 oxygen. So I'm going to start with my more electronegative terminal atom, which is fluorine, right? The halogen. So I'm going to start by making sure each fluorine gets an octet. So I'm going to just complete 1 octet at a time. I'm not going to slowly distribute. Like, we're not doing Hund's rule here in electron distribution for Lewis structures. All right. It'll end up applying just kind of naturally, but like in terms of how you do this, don't worry about that. Just fill out 1 octet for each terminal atom at a time. So fluorine currently has access to 2. And remember, every element wants access to 8. It doesn't matter if it's shared or its own, it just wants access. So far it has access to 2 out of the 8 that it wants through a single bond with sulfur. And now I'm going to add 6, 3 lone pairs of its own. Now that has an octet, and I have used up 6 of the remaining valence electrons that I can distribute. So now I'm down to 24. I'm going to go on to the next fluorine and fill it up all the way to an octet. Okay, so -6. Now I'm down to 18. Fill up the next one. Now I'm down to 12, right? Fill up the next one. Now I'm down to 6. Okay, fill up the next one. 1, 2, 3, 4, 5, 6. All right, and now I've used up everything. And we look at that structure and we're like, hey, that looks pretty darn good. All right. Now, one thing that you're going to notice here is oxygen is one of those unique elements that can actually tends to prefer being double bonded. It can stay as a 3 lone pair, okay? Or it can double bond. And fluorine, on the other hand, and actually any halogen, right, we know would never engage in a double bond, right? Any halogens never engage in multiple bonds. In multiple bonds where you have a double or a triple. All right. But oxygen is unique because it tends to be, it tends to be an element that likes double bonding. All right. So whenever you have oxygen as a terminal atom in general, you should be aware that there's always the potential that that could have a second resonance, another resonance form, another valid Lewis structure where you actually see oxygen fold in and form a double bond. Takes one of its lone pairs and form a double bond with sulfur because sulfur can handle it. Sulfur can have an expanded octet. Sulfur can go up to 10, 14, right? Electrons, because it has access to those D and F orbitals as a row 3 or greater element. So what you're going to see is that the actual structure for this compound does indeed prefer oxygen to only have 2 lone pairs, right? 2 pairs of unbonded electrons around it. And then it actually does like to have a double bond with sulfur. Now, you should automatically be perking up and saying, oh, how would I know which is the more valid Lewis structure? How would I know which is the more likely Lewis structure that would occur? That's where your formal charge comes into place, because now we technically have 2 resonance. The original structure I do in black with all single bonds, and the second structure that I created with the pink, right? Those are 2 valid resonance. So what you would have to do is you'd have to assign formal charge in order to determine which structure is the most valid using the formal charge rules, right? And the big idea behind the formal charge rules is 0. We just like as close to 0 as possible on an individual atom level and then as a whole molecule level, okay? So, but I'm not going to get into that right now because that's going to be our next problem. I just kind of wanted to highlight that. And let's move on to how do we draw Lewis structures for atoms or molecules that are charged? So remember a polyatomic ion? A polyatomic ion is a covalently bonded group of atoms that carry a charge and act like an ion, right? So it technically is a molecule, covalently bonded, but together, okay, they can behave like a different type, right? An ionic. okay, capable molecule. So that's kind of unique. I believe probably in class, I probably said analogy like when you're on a team, you all take on a unique as a dynamic, a team dynamic that can now accomplish something that you wouldn't be able to accomplish on your own. That's kind of the same idea behind polyatomic ions. Individually speaking, if you just write out the polyatomic ion, right, the single group of charged atoms that carry, charged atoms, they are still considered covalent. They're still considered sharing because that's how they're using their or distributing their electrons to create the bonds. But as soon as your polyatomic ion is written with another ion in an ionic bond, now we treat it like an ion. All right. So here we have hydroxide. I'm going to choose a super easy one, right? Just to remind you, to draw the Lewis structure, one, you'd want to just look at it and say, okay, things to notice. I have a charge of 1 minus. So that means that my total valence electron count is going to have an additional 1 electron added to it. And then 2, what is my central atom? Well, here we only have 2 atoms. So there's really no central. Here you can just tell there's already no central atom because it's only a 2 atom, what we call a binary molecule. It only has 2, okay, atoms connect, 2 different atoms connected, binary. All right. And something else though to note is, since usually when we have this, right, we don't have a central, but if we do have a hydrogen, they tend to always be terminal, right? Because they can never be the central. Hydrogens are always terminal because they can never be central because they can only have a capacity of 2 electrons max out. And that would be a terrible, terrible central atom for creating multiple bonds that other atoms attach to. So just like kind of small things. I know this one is a unique one because it's binary, it's a charge, and it doesn't always give the greatest picture of all these rules, but you kind of see consistencies, right? Technically, since there is the central part of the bond is like the center of the molecule, H is technically terminal, right? So just putting that out there. Anyway, let's go ahead and draw out the Lewis structure. Let's follow our rules. Okay, so we're going to count total valence electron count. So each oxygen brings in 6 and each hydrogen brings in 1. And we're going to add, right, that 1 minus electrons plus, the 1 charge. So we're going to get a total of 8 valence electrons considering the charge right here. So I'll just quickly write the charge, plus 1 because of charge. Count for the charge. And so we get 8 valence electrons. So what we do is you draw out a skeleton. Well, we don't really have a real central. So we're just going to kind of say the center of the bond is the central. And what we have is our hydrogen as a terminal and our oxygen. And that right there has used up already 2. So we have 6 valence electrons left to draw out that bare minimum skeleton. And then we fill in our octet. So I look at hydrogen and I already can tell it is unique because it already has its duet. It doesn't want any more, right? It wants the duet rule. We're not going to use the octet for hydrogen or helium. So that's satisfied. So we're going to distribute those those remaining 6 electrons to oxygen, give it its octet. All right. And remember how we said earlier that oxygen tends to like to make double bonds? Well, here it wouldn't make a double bond because here's why. Hydrogen, like a halogen, can never form multiple bonds. Okay. Never forms because it literally can only handle 2 electrons, access to 2 electrons. So if you tried to double bond it with oxygen, it would like basically implode itself. Like I don't think it actually would. It's hyperbole, but the idea is it's impossible. Okay. Hydrogen never forms a double bond. So here we do see that oxygen would stay as a 3 lone pair, structure in the bond. So this would be the structure. And what we would do is to finish it off, we'd have to show that it was carrying a charge. So we'd put it in brackets and write 1 minus on the outside. That is very important for you to write, to acknowledge there's a charge which made this particular Lewis structure possible. So please always bracket and write the charge outside of a charged molecule or a polyatomic molecule. All right. So let's go ahead and get into the resonance structures. So here we have O3. One of the key signs with resonance structures being possible is you have 3 atoms attached together that are the same, that are capable of engaging in multiple bonds, single or double, or sorry, triple or single, triple or double. Or you have a central atom that's connected to the same type of terminal atoms. And like the one below, NO3 is a central atom nitrogen, and it's connected to 3 oxygens that are also capable of double and triple bonds. And that's usually a good indicator that you have but the potential for resonance. So I'm just going to do the first one with you. And what we have here is O3 ozone. And we got to draw out at least 2 resonance structures. I'll draw it out 3 just to show you. Actually, no, I think there's only 2. Yeah, there's 2 resonance structures. Just kidding. And what we do is we follow, again, our standard Lewis structure rules. So let's go ahead and like count our valence electrons. So our total amount of valence electrons is going to be oxygen times 3, which is going to be 6 times 3. So we get a total of 18 valence electrons, okay? And no charge to account for. So I'm going to draw out my skeleton. Here, oxygen is the central atom because that's like literally the only option. And that uses up 6. So I have 12 left. So I'm going to fill out my terminal, get them to an octet. So that's minus 6. 6 left. 1, 2, 3, 4, 5, 6. And I run out. So as soon as I run out, now I have to look at my distribution of valence electrons and say, okay, how can I redistribute the electrons from this initial sketch to make sure that oxygen in the middle has its octet? So what I can do is I can take this pair of lone pairs and fold it in. All right, fold it in to create a double bond with oxygen. Okay. And did I miscount 6 minus 6, 12 minus 6, 12? Oh, gee willikers, I totally miscounted. Okay. Apologies, guys. I'm sure all of you wrote that down. I apologize. I apologize. My brain and my mouth was talking way faster than I was actually processing. So, I made a mistake and I wrote 6 instead of 4. So now I have 14, and then I would have done the 6 for the first set of oxygen terminal atom, and it would have left me with 8, then another 6, and I would have been left with 2, and then I would have put 2 on the central. And now I have, okay, I've used up all my electrons. I apologize. So I overcounted my initial use of valence electrons, which left me with not enough to make the correct Lewis structure. So make sure you can count better than your teacher. Okay, so what we have here then is now what I would do is I'd look and say, how can I, because I can't add anymore and I can't take away anymore. This is what I have to work with. These are the electrons available to me. I've put them all somewhere, and now I'm going to rearrange them. So now what I'm going to do is I'm going to take, like I said earlier, I'm going to make sure the central oxygen has its octet by folding in one of the lone pairs. Okay, one of the lone pairs to create a double bond with one of the terminal oxygens. So that gets me O, 2, double bond, okay. 1, 2, 1, 2, 3, 4, 5, 6, okay. And so that's one resonance structure right there. Now, I could technically also fold in spatially from the other oxygen. I could do the other oxygen. So while they are chemically equivalent, because they're all oxygen, while they reactivity wise, they are equivalent in nature, spatially wise, and you're going to learn later in chemistry that how the 3D structure and where certain atoms are spatially is actually incredibly important to their behavior. Spatially wise, the right oxygen is theoretically different than the left oxygen in terms of how it fits in the universe. So we could say that the other resonance is that the other oxygen folds in and produces this structure. And if you're like, it doesn't make a difference, it will at an advanced chemistry when you go to college. So it is important to recognize that even though they behave the same, chemically equivalent, because they're both oxygens, these terminal atoms, they are spatially different. All right, giving us a second resonance. All right. And also, of course, fulfilling all of the Lewis structure rules that we need, still maintaining the octet, still maintaining that certain atoms can form double and triple bonds, still maintaining the concept that we can't pull more electrons out of nowhere. We have to use what we originally had brought in by each atom. All right. So that's kind of your overview. let's do one formal charge problem. So remember, formal charge is the method where we assign essentially a fake charge. We assign a fake charge to each atom in a molecule or in a structure in order to determine which Lewis structure is the most valid. Okay, which Lewis structure is the most probable that an atom will, or sorry, a molecule will take on. And we have a very unique notation for it where we write the sign and then the number to differentiate us communicating charge. Charge is number then sign. Very small little detail, but very important. And the overall equation for formal charge is to count up the valence electrons that the individual atom would bring in that structure and subtract the dots and the lines from around it. Okay. So let's just do the first one here. We have the structure for CSCO or OCS, whichever way you want to write it. And what I'm going to do is I'm going to assign a formal charge to each atom because that's the trick. You have to assign it to each atom in order to understand how together those individual atoms create the best or most likely to be found molecular structure in the universe. So oxygen initially, okay, oxygen formal charge in this structure. I'm just doing this structure. Okay, number one structure. Oxygen initially brings in 6 valence electrons, but it has 4 dots and 2 lines around it. So what we get is 6 minus 6, 0. Let's look at carbon. Carbon initially brings in 4 valence electrons, and it has 4 lines around it, no dots. So we get a formal charge of 0. So we would do plus 0, plus 0. And sulfur, okay, brings in 6, and it has 4 dots and 2 lines around it, so 0. So that's kind of how we would solve the process. Now, if you do numbers 2 and 3 on your own, all right, you're now going to have to make an argument about which one's likely to form. Here's my suggestion for writing up the argument. Remember the kind of rules of formal charge is 1, we always want the sum of the formal charge for the sum of the individual atoms formal charge in a molecule to add up to 0, or the charge of the overall molecule, or charge of overall molecule, right? And then of course we want the individual, okay, formal charges. We want the individual formal charges to be closer to 0. Really like 0. That's a really stabilizing indicator, a quantitative indicator. All right. And then we have a couple other rules, like let's say you have to form a charge, like you can't just keep everything at 0, and you have to have an individual charge, positive or negative on an atom. We want the more negative formal charge to be on the more electronegative, the more electron greedy atom, right? But there's all those rules that you go over in your notes, right? These are probably the 2 most important. So for determining which is the most legitimate which is the most legitimate resonance structure. But go ahead and try doing number 2 and 3 on your own, and then try crafting an argument, okay? It's really important that you practice those explanation skills, all right? So let's go ahead now and move on to our AP problems. So we're going to finish up problem long FRQ. We're going to do the next portion of the long FRQ. And remember, long FRQ is about 10 points and worth allotted about 23 minutes by the AP. So in this long FRQ, what we have here is we've previously answered some questions about bonding and diatomic elements and the likelihood of another element of a similar family behaving in a similar way. And now we have in the box to the right, draw a complete Lewis structure for C2CL4. So remember, one of the tricks is that carbon is often your central atom. Now here we see something interesting. We have 2 seeds, okay? Here we have an interesting case where 2 carbons kind of act as the general central, okay? And then we have CLs around it, all right? If you're like, how did I know that? It's kind of a trick or trade. I would just remember that carbon tends to be the central atom. And if you have multiple carbons in a molecule, they tend to be the relative centrals or the linked centrals to one another, okay? They just tend to stay central. And they linked to each other. That's kind of just a general trick, is that carbons tend to link to one another and then everything around it follows. So here I have this structure, and oh, I totally cheated for the total valence electron count. Sorry, guys. Total valence electron count, you guys should always start with your total valence electron count. We have carbon, each carbon brings in 4, so I got 4 times 2, right? And each chlorine, okay, brings in 7, so 7 times 4, giving me a total of 28 plus 8, which is 36 valence electrons. So for my skeleton structure that I just sketched out, I've used up 2, 4, 6, 8, 10, okay, valence electrons. So I have 26 left. Now what I do, of course, is I start filling out my terminal, and I complete an octet for each terminal atom, one at a time. So this chlorine originally had access to 2. It wants 6 more, so I give it 6 more, right? 1, 2, 3, 4, 5, 6. Okay, another 6 more. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, and that's 6 times 4. All right, so I've used up 24, so I have 2 left. So I go now into the central. Now I start taking care of the central atom, making sure it's an octet, and I kind of max out. I only am able to give one of those relative central carbons an octet. So now I look at my structure and I say to myself, okay, what can I do to make sure that the other central atom has an octet? Well, we know that when we look at chlorine, we can't have chlorine fold in and create a double bond, because chlorine is a halogen, and halogens, right? Halogens never form double or triple bonds. Okay, so we know we can't do that. But what we can do is we do have carbon, and carbon is actually completely capable of forming double and triple bonds. In fact, it's one of the most common things that carbon does. It's a single, double, triple bond happy. It's a bond happy atom. Like, it just loves making bonds. So what we're going to see is everybody has their octet. Every terminal atom has their octet. It's just one of those carbons that doesn't. One of those central carbons doesn't. So what we're going to do is we're going to have one of those carbons, wherever you designated that lone pair to be, we're going to have it fold in to our structure, and we're going to form a double bond between the 2 carbons. Now, remember, I'm not adding or subtracting any electrons here. I'm just redistributing what I have available to me. And now what we see is that each carbon, each relative central carbon, has an octet. This one does 2, 2, and then 4 shared, check. And this carbon does, the rightmost carbon does 2, 2, and 4, check. And so what we get is we get a double bonded, okay, carbon structure with 2 carbons acting as essential. Okay, so that is how we would figure out the structure for this molecule. A little bit more complicated. It's why I wanted to go through it with you, because you're going to find that there are a lot of these kind of unique Lewis structures that the AP will ask you for. The big idea is that don't ever think that halogens create double bonds. And 2, don't forget your carbons tend to like to be attached to each other if there are multiple of them. All right. So there's that AP problem. And let's just go through one more AP problem. I'm going to cut it off after this one. So here, question number 2 is a short FRQ. Short FRQs are designated about 9 minutes and worth 4 points on the AP exam. So what we have here is consider the carbon dioxide molecule, CO2, and the carbonate ion, the polyatomic with a charge, right? Polyatomic molecule. And draw the complete Lewis structures for each species. And then account for the fact that carbon oxygen bond length in CO2, carbonate is greater than the carbon oxygen bond length in CO2. How can we explain that? So first and foremost, okay, let's draw out the structures. So I'm not going to go through how to draw the Lewis structures so much now, because you guys have had several walkthroughs through class and the previous problems if you watch the conceptual. If you're still struggling with Lewis structures, just watch the conceptual video, okay, the first portion of this video. That's what they're for. That's where that first half is, to really slow down and give you guys a second opportunity to go through things step by step. I'm kind of done explaining this so many times, so I'm just going to go ahead and draw out the Lewis structures. So if you followed all the Lewis structure rules, you would get that carbon dioxide, okay, is this structure, and then you would get carbonate ion is this structure. Okay. And if you're like, how did I know? Okay, formal charge, buddy, formal charge. And of course, I have, right, my little brackets to represent that the only way I could get that Lewis structure is if I account for having a 2- charge, giving me 2 more valence electrons available to me. You could draw any resonance of that. It's all valid, right? The resonance for carbon or carbonate is all valid. And what I need to account for is Y is, okay, the carbon-oxygen bond length in CO2 greater than the carbon oxygen bond in CO3 2- greater than the carbon oxygen bond in CO2. So remember with bond length, right? With bond length, okay, the greater the bond length, the weaker, okay, the bond strength, and usually the lower the bond order, right? So single bonds are always going to be longer than double bonds or triple bonds, all right? So when we look at this structure, we know that technically carbonate has 3 resonance, where we can kind of create like a double bond across all the molecules. All right. And so what we see is when we have a resonance where we can move that double bond around, we get a bond over between a single and double, which is about a 1.5. Okay. Representing a single half double bond. And then with carbon dioxide, we have a double bond. And the bond order for this would be 2. Okay. So what we see is we have a higher bond order with CO and CO2 than we would CO and carbonate. So because, okay, we have a higher bond order, we would expect, okay, greater attraction, or I could say strong, we would expect a stronger bond and shorter bond length. All right. So that's kind of the explanation for that. That tends to be a pretty common kind of FRQ, MCQ explanation. And that's all I have for you today. Sorry about problem B2. I don't know why it got like stricken through, but you're definitely going to do that problem. Like that's totally on the new one, totally a problem that you're going to do. So best of luck, you guys. I know we're starting to really ramp up. Unit 2 is kind of the real push into the rest of our 9 units. So good luck, everybody, and practice, practice, practice. Your workbook problems are going to be your savior. So good luck. Ask me any questions, schedule times, and please come to seminar and craft out times to meet with me or the awesome TAs that have volunteered to help you. So bye, guys.